Uh, about myself, I work in a group in IBM called CODE, Center for Open Source Data and AI Technologies. And CODE essentially has a set of dedicated open source developers contributing to end-to-end data and AI lifecycle space. We have a project, some of them which are homegrown, which we put out in the open source, some of them which are in open source, which are strategic to IBM, where we contribute. But the group's goal is essentially be focused on open source, right? At this point, we have approximately 40 plus developers um, in the Code group spread across our San Francisco and San Jose offices. But like there are projects like data asset exchange or model asset exchange, or our trusted AI projects around explainability, bias detection, adversarial detection, which we had put out in the open source, including a very recent one, which is called Elira, which is an extension on top of Jupyter Lab. But then there are also projects, right, as I mentioned, where we contribute heavily in the community. So TensorFlow, Spark, PyTorch, and Kubeflow definitely fall into that specific area. So I lead IBM's engagement into the Kubeflow community. One of the committers there. One of the major focus areas also, which I do tend to drive within IBM, is our alignment with open source data and AI, with the activities going on within Red Hat. Um, I chair our Trusted AI committee, Linux Foundation AI, and work very closely with that community, with our Trusted AI open source projects in that space. Also, there is an MLOps SIG, right, which I run as part of the CD Foundation, which is focused on the CI/CD aspects of the machine learning pipelines. And here is our team, the excellent team, right, which is contributing to Kubeflow. Now, more than around approximately, on the last count, we have more than 25 IBMers who have contributed to Kubeflow. Now, some of them, do it on a more dedicated basis. Some of them, have particular areas of interest for a particular time frame where they come and contribute, and because of those excellent contributors, right, IBM is now the second largest contributor, and not now, right, it has been the course for the last 1 year, right? We have consistently been the second largest contributor within the Kubeflow community after Google. And this is, the data which is coming from Stackalytics, right? But also if you look at the CNCF DevStats dashboard, that tells a similar story. But we are not the only contributors, right? I mean, there has been excellent work being done by, a lot of the participating companies like Cisco, Erecto, Amazon, Cerdan, Bloomberg, contributing heavily to multiple aspects of Kubeflow, either within a particular domain area. And they're all bringing, great set of technologies together and putting up this platform together for the community. So when we look at Kubeflow, right, there are two guiding principles, right, behind this. When you look at the vision and the architecture, one is around, the first-class citizen of Kubernetes, right? Now, what lends itself to that is then, the architecture principles and paradigms which flow into that is most of the Kubeflow components are architected as Kubernetes custom resource and custom resource definitions, right? So totally Kubernetes architecture allows you to extend Kubernetes APIs and provide your own implementation. And what happens is, because of that, is you can use kubectl, right, which is the command line which the majority of the Kubernetes community uses. And it's not, overstating the fact that like majority of the enterprises in the world, for when they're looking at cloud native, they are interacting with Kubernetes in some form or fashion, right? So that lends itself nicely to that. But the second part of that architectural principle is, yes, there is a strong community which works with kubectl and Kubernetes APIs, but this is a platform primarily targeted for data scientists, right? So we make sure that, there is a Python interface to majority of our components. There are Python SDKs which are available, and there is a first-class integration with Jupyter notebooks to leverage them, right? Because ultimately the consumers of this platform are data scientists. Now the providers are essentially the folks, right, who are standing up these Kubernetes Kubeflow clusters and then maintaining them. So, that part resonates with them. So I think this, you can see the vision was to bring data scientists and MLOps teams together to build that one platform which can serve the needs of both. And it will be heartening to say that, we've been pretty successful at doing that. As I mentioned, the community is growing, and I mentioned, the stellar contributions being done there by the likes of, Erecto, Cisco, Bloomberg, Selden, NVIDIA, and quite a few of them contributing to multiple aspects of Kubeflow. And this is a bit of old statistics, right? But this has been on the upswing since the project started. The other aspect of it is that Kubeflow is now heavily, being focused towards multi-tenant, multi-user isolation model, where you don't need a Kubeflow install per team or per set of users. You can have, highly distributed install of Kubeflow, which is then, multi-tenant, and you can have isolation based on users and groups, which are then backed by, in a lot of cases, the namespace isolation under the covers. So each of these teams then get their own, instances of the notebooks, or they are able to run their distributed training jobs, serving, etc., in their own dedicated namespaces. Okay, so the build part of machine learning lifecycle is very important, right? So build is where we do the initial development of the model. We do distributed training. We are, selecting our set of hyperparameters. And that's where, also there is a strong focus in Kubeflow. So as I mentioned, for Jupyter, right, which is right now the default standard for a lot of data scientists, Kubeflow has built what is called Kubeflow notebooks. So essentially a custom resource and custom resource definitions to actually instantiate Kubeflow notebooks on top of Kubernetes clusters. And then, what that allows you is, be able to leverage the underlying Kubernetes integration, working with CPUs and GPUs, be able to leverage the underlying persistent volumes, etc. So brings all the underlying capabilities of Kubernetes exposed through this Kubeflow notebooks. And then, this is also integrated with our common services, which is Istio, Dex, etc., right, for authentication authorization. So each of the users get their own dedicated installs of the notebooks right within their namespace. The other thing which we have sort of focused on also is that, we are keeping the base images smaller, and what we have seen is moving away from Jupyter Hub to this, we have seen far fewer crashes, a very nimble and agile, Kubeflow notebooks environment. Right, so this is how the Kubeflow dashboard looks like. When you go there, you can see a list of the pipelines, notebooks, documentation around how to get started. You can go to the notebook server tab. You can select, your namespace in which you are operating. It will show you the notebooks you have. You can essentially then, either launch a new notebook as well. And when you click on that, it takes you through the dashboard where you are able to select the underlying, the infrastructure constructs, because, you want to specify, so you have that level of control whether you want to run it on a GPU or a CPU, what persistent volume you want to use under the covers, etc. Right, and the other aspect, as I mentioned, was that you can launch your own Jupyter notebooks after this. So now, once you have the initial build part, you have your initial model, right? Then you start looking at the next part of it, right, where you essentially are looking for distributed training or hyperparameter optimization, right? So specifically in the context of distributed training, Kubeflow provides, the first class citizens, TensorFlow, PyTorch, distributed training operators, again, designed as Kubernetes custom resource definitions. And then, if you are not using the native TensorFlow or PyTorch distributed training algorithms, right, there is an operator which is based on Uber's Forward project, which gives you the capabilities to leverage MPI protocol. And I will talk a bit about that as well. But that's not all, right? I mean, TensorFlow, PyTorch definitely are dominant parts of this ecosystem, but depending on the geography you are in, depending on particular community, there are folks who are using MXNet heavily. There is Chainer, which is very popular in Japan. For example, MXNet obviously has its own strong user base as well, right? So Kubeflow tends to go broad, and there are operators. Right now at this point there are 6 operators which are going typically broad across these frameworks. And if you're wondering why scikit-learn is not there, right, which is very popular in the machine learning community, I think it's by virtue of it, scikit-learn doesn't lend itself to a distributed training mode, and that's one of the restrictions why we don't have it on the platform. But other than that, all your major machine learning or deep learning frameworks are there. Now, as I mentioned, what is happening under the operators when you actually peel, they're essentially optimizing and ensuring that, the distributed training algorithms which are coming inbuilt with these frameworks. For example, TensorFlow uses a parameter server approach where when you are distributing the training across multiple worker nodes, all the weights and the gradients which are being synced are being sent to a parameter server, and the parameter server is then distributing it to multiple nodes and keeping all of them in sync. Now you can obviously scale the parameter server itself, right? And so this is the protocol which TensorFlow uses, right? So that's what is inbuilt into the distributed TensorFlow training operator. Obviously, then ensuring that the right consistent consumption of the GPUs, etc., under the covers. But if you're not using, for example, the native TensorFlow distributed training platform or algorithm, and you want to use something like MPI operator, which gives you an already used algorithm. So essentially, in this case, there is no parameter server, right? So all your worker nodes who are getting, who are performing the training jobs, they're syncing the weights and the gradients amongst themselves using, the already used algorithm. And this is essentially a technique which has been made very popular by Harvard, right? They use MPI protocol under the covers, and that also enables, very strong communication from GPU to GPUs, either within a single machine or spread across multiple machines. Right, so that is functionality which the MPI operator covers, and MPI operators, by virtue of having Harvard under the covers, can support TensorFlow, PyTorch, and other operators as well. So, okay, we talked about distributed training and the algorithms and the different operators, right? I've not gone into detail on each of these operators, right? There is a session tomorrow as well, where we will be, doing a deeper dive into them. But one of the steps also, which is very important during the build phase, is hyperparameter optimization, right? So Kubeflow has a project in this space called CATIB, which is essentially, excuse me, focused on this particular area, and supports multiple, hyperparameter tuning algorithms: random search, grid search, hyperband, Bayesian optimization. And definitely it also starts extending into neural architecture search. So there are a couple of algorithms which we are plugging in there as well. Now this is one of the projects which is very popular in the space, where people are looking to find the right optimum set of hyperparameters. So it also has its own dashboard, so you can go to Kubeflow dashboard. When you go to CATIB, you can look at either provide a YAML, or you have a form-based approach where you can specify the parameters on which you want to optimize the number of counts or runs you want to run for it to find. And once you have submitted your job, you can actually monitor the progress of it, right? So you can actually go and look that for the parameters which you have asked it to optimize, how is it optimizing around it. It will run number of trial runs based on the count you have specified and try to find the optimum rate, right? So in this case, we are optimizing for loss, right? And we are saying, reduce, we want to reduce the loss based on these hyperparameters. So if you look at it, right, it comes with the metrics based on the batch size and the learning rate, right? And you can look at the more details around it. Again, there is a deeper dive into this tomorrow as well, right? Folks who are interested in this, right, with a much deeper demo into this particular part of Kubeflow. Okay, so you have built your models using Kubeflow notebooks. You have, found the right set of hyperparameters, choosing one of the algorithms which CADIP provides, and then you have run distributed training at scale, and you've produced your model, the candidate model, which is ready for production, right? Probably we think our job is done, but for a lot of the production use cases, the real job starts at this point, right? Having a production model serving platform is critically important, right? Because that's where a lot of the cost parameters come in as well. Because and most of the models, right, heavy duty models, they are running on expensive GPU resources, right? So you want to constantly make sure that they're not over or underscaled, right? If they're not getting utilized, they are not hogging, the underlying GPU infrastructure on which they are served. You definitely want to have a very solid and robust monitoring stack around it, right? Look at the traces, request traces, etc. And then, given the experimental nature of machine learning, one of the things which you will be doing constantly because your data set has changed, or you have found a drift in the model, there is an anomaly, or the model is giving biased results, you will be essentially running this again and again, right? So you are essentially rolling out new versions of the model at much more frequency than you typically do in the application world. And if you're doing that, you want to make sure the rollout safe. Can you roll back? Can you incrementally increase traffic on your next version of the rollout, and as you are ensuring everything is right. Now models are also deployed. You want to make sure the predictions, can it support multiple protocols, HTTP, gRPC, Kafka, right? And is the data plane standardized? Now a lot of people miss the importance of this particular point, because if you are deploying model, for example, on, let's say, any of the major cloud providers model machine learning platform, right? You are particularly bound to that, the API set, in terms of, calling models for predictions, explainability, etc., right? And ideally, in an ideal world, you would want to move models across, right? So I want to move it from IBM Cloud to Amazon to Google to TensorFlow serving to KF serving to Selden without having to rewrite my client, right? So that's where the standardization around the data plane API protocol plays a big role. And obviously, I mean, the multiple frameworks, right? You want to be able to bring all the machine learning and deep learning models and be able to serve them. The other aspect of it is, it's not only predictions. Your model should be giving explanation, should allow you to wire up custom pre-processing and post-processing code, right? Because typically models don't only take, I mean, most of the models take, for example, let's say, tensors as inputs and outputs, but what your end user is giving you probably is an image. You're probably giving back as text as an output, right? So having that capability to plug them in and selectively choose where to run what, right? So you probably want your predictions to run on GPUs, but you want your pre-processors or post-processors to run on CPUs. So a lot of these capabilities are required to serve models in prediction, and that gives you the scale of the problem, right, which needs to be solved in this particular case. Now, the story, I would say around a year and a half ago, was that, Selden has started doing, a lot of great pioneering work in this area. We gave a talk at, it was the end of 2018, Tommy and myself, we gave a talk on serverless model inferencing at KubeCon, which was heavily attended. And, that was essentially, using Knative under the covers. One, the founder of KF Serving, LS, he was also, there in the talk. Then, Google has been doing great work around TensorFlow, TF Serving. So a lot of the work was happening, right? But there was no consistent standardization across this field, right? So what we did somewhere towards the first or second quarter of last year, I would say, we got together and said that, all of us are doing and taking it in our own way, right? And it is time to come together and build something, right, which can hopefully, start becoming the standard which the industry requires around model serving. Right, so that was the genesis of what we call KF serving. So essentially built on the Kubernetes native stack, leveraging Istio and Knative. And our initial focus was, around 80% of the use cases, which is, single models rollout and update, making sure, the founding principle, which is the serverless machine learning inference, the rollouts, the canaries, right, they remain intact across them. And then, providing capabilities to plug in your pre-processors, post-processors, explainability, and then now moving forward into other areas like bias detection, drift detection, etc. So as I mentioned, right, one of the key characteristics of machine learning world, very experimental. You are probably rolling out newer versions of the model much more frequently than you roll out an app. This is not a world where you roll out for 6 months and then you are happy when before the next version comes. So that's where, having the concept of default and canary becomes very important. And this is one place where we also differed from Knative, where in Knative's construct, if you're aware of it, if you change a revision, then it becomes a new configuration. In this case, we allow multiple revisions before you can finalize, for example, your canary configuration or your default configuration. And then, you can split traffic across them, right? So if you're rolling out a new revision in your prod environment, you can say, okay, let's just start with 10% of the traffic, make sure everything is good. And then, we can incrementally update the traffic. We, by virtue of it, right, we are ensuring that we are supporting the major machine learning and deep learning frameworks. So TensorFlow support, for example, is enabled by TF serving. We have NVIDIA's Triton server, renamed at this point to Triton, right, which gives a strong performance for models which need to consume GPUs, right? So that's available for PyTorch, XGBoost, and scikit-learn. We have developed our own custom servers, right? But there is also discussion going on with AWS for them to be able to contribute the latest Torch serve, right, which has been introduced in the PyTorch community very recently. And then Onyx runtime, which was contributed by Microsoft to serve Onyx-based models. And we support, different kinds of storage. S3, any S3 compatible storage is supported. But then, Google Cloud Storage, Azure Blob, persistent volume claims if you're running in on-prem. So essentially, one of the other things which we ensure is a first-class citizen beyond, the canary aspects of is the serverless aspects, as I mentioned, right? So that's where, we leverage the underlying Knative constructs of, activator and autoscaler heavily. Right, so activator is essentially the component responsible, right, for buffering your request, and autoscaler is the one, right, which is monitoring the metrics on the activator as well as the queue proxy, and then decides when to scale or, when to scale down, right? So essentially, as I mentioned, if you have configured scale to 0, that means if there is no traffic for your configurable period of time, the model scales back to 0, releases your infrastructure, and then, as traffic starts ramping up, the auto scaling starts kicking in. Right. This is also request-based scaling, which is much better than, relying on CPU and GPU-based scaling, which can be, very sporadic, and there is no consistent mechanism around that. Right. So typically, by virtue of combining these things, you get a strong control over, canary rollouts, traffic splitting, traffic percentage control, auto scaling, scale to 0. So all these capabilities, get enabled as part of the KF server. Now, another area where I do want to highlight a bit of a focus is Transformer, right, which is responsible for the pre-processing and the post-processing. And as I mentioned, the advantage of having a pluggable transformer is that, you can have pre-processors or post-processors run on CPUs versus your predictor, right, which is doing much of the heavy duty lifting that can run on a GPU, right? The other aspect which we have integrated is payload logging, right? And that enables us to give much more advanced capabilities around model management and monitoring, right? So for example, because the payload logging, which has been implemented using the standardized cloud events protocol, we can do things where we can gather your payload requests and responses. And based on that, right, we can run analysis to figure out, if there is a concept drift, if there is an outlier, is the model giving or is the model vulnerable to adversarial attacks? And then based on that, right, you can do alerting, right, whether you need to retrain or to take certain action. Right now, all these capabilities, but the data scientist sees a very simple YAML file, right? That if you're using kubectl, right, if you don't want to see YAML file at all, you can use a Python SDK, which KF Serving provides. So don't get exposed to YAML at all, right? I know a lot of us don't want to see the YAMLs, but typically, you get all these capabilities behind the scenes around scale to zero GPU or scaling, safe rollouts, etc. So this is a chart which is sort of summarizing a lot of the capabilities which come as part of KF Serving, right? So I wouldn't go through them. I mean, the slides are available, and tomorrow we have a deeper dive session, right? Where I will dive into quite a bit of these capabilities. There are a lot of more exciting features coming on, right? The one probably where I'm most excited about is model chaining or model graphs, where you can chain multiple models together with the output of one going into the next, right? So that's plus also multi-model serving, so being able to serve multiple models, so not having a one-to-one relationship between Kubernetes custom resource and a model. So multiple models can map to one custom resource, right? So that handles and lends itself very well also to and enhances the scaling features of it, right? And from an IBM perspective, right, we will also be focusing quite a bit on integrating our trusted AI projects around explainability, bias detection and mitigation, adversarial detection into KF Serving features. Okay, so we talked about building your models using Kubeflow notebooks, doing distributed training and hyperparameter optimization as part of the build phase, and then deploying your models in production using KF Serving, right? So obviously, I mean, there are still pieces which we have probably not covered. There is a lot of custom tasks which you plug in between these things, and in the end you need something, right, to bring this whole life cycle together, right, which can automate as much as possible your build, train, validate, and deployment life cycle, going even to the management and monitoring, right? And that's where Kubeflow pipelines comes in. Again, I would say at this point, the most popular project into the Kubeflow community, and aligns with the larger Kubeflow vision, which is built on top of and for Kubernetes, right? Leveraging all the underlying scalability, resiliency, and the core architectural paradigms, but ensuring that it's consumed by data scientists. So by virtue of that, right, there is a Python DSL which has become very popular, to craft your pipelines. You can craft your pipelines using Python, and then but also be able to leverage the underlying Kubernetes constructs. Like in most of the times, if you're running training, for example, on Kubernetes, your data is probably running in a Kubernetes volume, right? So all those config maps, secrets, Kubernetes volumes, containers, they are exposed as a first-class citizen into that Python DSL, right? So data scientists don't need to understand the underlying infrastructure bits there. Now, if you look at it, this is a sample of the Python DSL. In this case, this is running TensorFlow data validation job, running pre-processing, then using distributed training, running TensorFlow, and then running model analysis on part of it, finally deploying it on KF Serving. Now, in a sense, this is running the whole end-to-end life cycle, right? Starting from data validation, right? I mean, you can do things like schema generation, etc., as well, and plug it into this. But if you see the powerful nature of this code, right, you probably are seeing around 15 lines of YAML, allowing you to not Python, allowing you to automate the whole end-to-end, the machine learning lifecycle. That's where Kubeflow really shines. But then once you have crafted your pipelines, you can upload them on the dashboard. You can bring your custom ROC curves or statistics and graphs which you need to display as plugins, right? You are going to be creating a lot of these pipelines, right? This will proliferate, again, going back to the machine learning experimental nature, and you can have very solid and robust pipeline versioning here. Artifact tracking is enabled because this is something, again, very important in the context of machine learning, where all your lifecycle pipelines are producing a lot of these artifacts, and you want to be able to go back to those artifacts produced, investigate them, and ensure they are consistent with the mechanisms you have defined. And then also lineage tracking, right? Which is very, very important in machine learning, where tomorrow if my deployed model denies someone an admission in the university, and someone claims, okay, on what criteria did it deny, right? And we find out, okay, is the model doing something wrong here, right? Was it not consistent? Then you need to be able to trace back the whole lineage, right? On what data set it was trained on, what were the hyperparameters used, what was the TensorFlow version used, right? So be able to say, okay, where the problem lies, right? So the whole lineage tracking is enabled. This is, high-level view into the Kubeflow architecture. The entry is enabled primarily by Kubeflow pipeline SDK to compile, upload, and launch. But there is also a dashboard, hugely popular to upload and launch your pipelines and look at the lifecycle as they are running through it. Then you have, the TFX SDK, which is also getting merged. Both KFP and TFX SDK are, on the verge of becoming one, which will, is an entry point. But for now, you can just use the native TFX SDK and launch with Kubeflow pipeline as a backend as well. And then under the covers, right, majority of the CI/CD is by default, done by Argo in the default version. And then, a lot of your metadata is being stored in MLMD, which is model management database to store metadata and characteristics around it. There is a MySQL database as well, but that is more focused on storing data related to the UI constructs of Kubeflow pipeline. All your pipelines, etc., which you upload, they go to an S3 compatible object storage. Right. And now once you have this up and running, right, as I mentioned, they allow you to tie this whole life cycle in an end-to-end fashion, right? So you're not only able to run, for example, training here. In this case, for example, which you see on the screen is, I'm not using even any of the training operators, given that this is a scikit-learn model. I'm just training it using a custom, wrapped inside a custom Jupyter notebooks, then deploying that model on KF serving, and then we launch post-processing, scoring clients, monitoring clients to ensure that the deployed models, we are able to send requests, etc. So I think what we have established so far is Kubeflow, by virtue of bringing all these disparate technologies together. Now there are few things which I didn't talk about, like for example, there is also a Spark operator which is available into the Kubeflow community if somebody wants to deploy that, right? But by virtue of bringing all these projects in the machine learning space, right, it tends to provide this whole end-to-end machine learning and AI platform. What are we doing internally, right? There are multiple teams which have adopted or using Kubeflow pipelines to be more particular within IBM, right? But definitely, investigating other parts of Kubeflow. And I wouldn't go into, different parts of the IBM umbrella, right? But something which is, more for external consumers is, which essentially, we have decided to base our Watson AI pipeline story on top of Kubeflow pipelines, right? And that essentially brings together the pipelining aspect of Kubeflow to Watson. That's what we are working towards. Now, that doesn't mean that, this is something bringing in Kubeflow all in, but essentially Watson has a lot of components around training, Watson Studio Deep Learning as a service, Watson Machine Learning, which is a product on model serving, Watson OpenScale, which is another product which we have around the model management, as we call it, around explainability, drift detection, bias detection, etc. So these pipelines will become, the technology to run that end-to-end life cycle. Plus, there are products which we have around auto AI, data refinery, right? So the goal is to bring all of them together, but tie them through the Kubeflow pipeline layer, right? So as I mentioned, for example, if you look at this one is going through our data refinery, auto AI, Watson machine learning products, and doing the tasks, right? So this is a work which is in progress now, but this is not Kubeflow pipeline as is, right? So one of the goals which Watson gave us was essentially to ensure that we run this on top of Tekton backend instead of Argo. And the primary reason being that IBM is strategically invested in Tekton. IBM Cloud supports Tekton pipeline. OpenShift pipelines productization is also based on Tecton, right? So those are the, I would say, the stronger business reasons. But in general, what we feel is, there is a more composable and reusable architecture as part of Tecton, where the tasks and the task runs, they are independent entities and independent CRDs within the ecosystem, which allow you to run these things individually without tying it to a pipeline, right? So it lends itself to a better composability as well as reusability from that perspective. So when we started this work, right, we divided it into phases. Phase one was essentially, let's start with KFP SDK and compile it. And once we compile it to Tecton, we can run it on Tecton. Phase two was, instead of going to Tecton directly, let's upload that compiled output to Kubeflow pipeline API and engine and run it through that, right? And, not to deep dive into the details, right? But when we started, this required, bringing together multiple teams within IBM, outside of IBM together to get this done, right? But the net result of that is that, we have now delivered the second release of Kubeflow pipeline and Tecton project, which allows you to use the same KFP DSL, right? There's some restrictions, but beyond that, right, majority of the Kubeflow pipelines which you have run will run as is. You compile it to Tecton, take it to the same engine, right? So you get the same experience. In this case, this is a simple pipeline which goes through Watson Studio, Watson Machine Learning, Watson OpenScale. But if you see the YAML which is backing it, on the Kubeflow pipeline dashboard is the Tecton YAML, right, which brings the pipeline spec, the task spec, the condition spec all together into one single YAML. So that's, backing this particular DAG. The second thing is, if you are using, logging by default, right? That's the key characteristics of Kubeflow pipeline dashboard, right? So you again get the exact same experience in terms of being able to space the logs. But if you are also using more advanced features like artifact tracking or lineage tracking, that's all now enabled with Kubeflow pipeline and Tecton backend, right? So pretty strong capability. I'm glad to say that, we have not delivered it. And it also enables, even if someone is just natively working in the Tecton community and needs a Pythonic way of defining Tecton pipelines, right, they can just use it within that context. But for the overall Kubeflow community right now, this is available as an option. And one of the typical pipelines which we use to demonstrate, going through Kubeflow components to run hyperparameter search or distributed training as the MNIST pipeline, and serving it through KF serving, right? So that's also, working end to end using the Kubeflow pipeline and Tecton backend. And depending on the time, I will hopefully be able to, go through some quick demos on that side. Okay, the adoption aspects of it, right? So I mentioned, right, and I will talk about it in the context of IBM, right? As I mentioned, right, multiple teams within IBM who are finding value into the Kubeflow pipelines, and they're using it, as well as, we are working on productizing it. But, we have been also working with quite a bit of customers, right? So for example, we worked with Telstra. We gave a talk at Think in terms of building their Kubeflow environment on a mix of x86 and power infrastructure. So, if you're interested in diving into the details of it, you can go to that particular talk. And the future of that particular work is that, we are now going to be moving, the control plane to OpenShift. And then, the rest of the data plane will be running on a mix of x86 and power. Another customer which we work with, on which we gave a public talk, and it's again, publicly referenceable, is through the Think session, is Yara, which is into the digital farming space. It's a company in Norwegia. By the way, Telstra, if you're not aware, the previous one is the largest telecom provider in Australia. And then, I think one of our first adopters within IBM was Watson speech to text. They have been using it to automate quite a bit of the operations behind Kubeflow pipelines, right? Where we are getting a lot of the audio data on our publicly hosted Watson speech to text APIs, converting it to, splitting that audio, converting it to data, then, doing merge, verification, training, analysis. But they are using the Kubeflow pipeline to automate some part of that process by leveraging our underlying, core native other eco products within IBM. Okay, so now we talked about Kubeflow, right? One of the other things which I do want to introduce to the community is, something which Red Hat colleagues have been building, which is called Open Data Hub, right? And one of the terminologies, for example, which Red Hat uses is upstream, midstream, and downstream. And typically, this is terminology which comes from the oil and gas industry, where upstream is essentially the exploratory process, right, where you're actually trying to find oil on land or in oceans, right? Midstream is when you are actually now producing it, right? We are actually processing it, producing it, and it requires multiple people to come together. And downstream is the delivery phase, right, where you are actually in the selling, marketing, delivery phase. Now that's the terminology which is used, and as I mentioned, right, comes natively from the oil and gas industry uh, and goes through their life cycle. So a lot of the Open Data Hub, right, has been focused initially when it came out, right, there has been a stronger focus, I would say, on the data side. They also address, the ML and AI lifecycle, but very strong on, bringing technologies like Superset, Kafka, Airflow, PostgreSQL, MongoDB, all as a first-class citizen, Apache Hive, right, as a first-class citizen on top of OpenShift. And then they, work with the ISVs and the partners to actually amplify that effort, right? So, for example, working with NVIDIA on ensuring, the GPU integration within OpenShift is very huge. You're working with partners like Selden, where Selden is now available in the Red Hat marketplace. So that's how that ecosystem is particularly being leveraged. And if you look at the reference architecture, right, I mean, it goes across the layers which we are familiar with, and then maps technologies from the OpenShift ecosystem into that, right? A lot of the technologies will come natively, given that this is the OpenShift ecosystem. So a lot of the authentication, single sign-on, etc., get enabled by that. But then, bringing a lot of these open source projects within that space together and mapping it to layers like data in motion, storage, data analysis, AI and ML as well. Okay, so I was talking about, the technologies which Open Data Hub has mapped, right? Now, what's the relationship between Open Data Hub and Kubeflow, right? One of the key things when, around the end of last year where Open Data Hub started looking at, the Kubeflow and the strong focus on machine learning and AI side, right? And wanted to ensure, that becomes one of the linchpins, right, of Open Data Hub for ML and AI. And then, also offer capabilities to mix these components, right? So you can mix components from Kubeflow, which are very stronger on the ML and AI side, but also bring in things like Kafka, Superset, Hive, right, if you're deploying this. So one of the first things, right, which we did to enable that ecosystem, because a large part of OpenShift ecosystem, works through operators, right? We created an operator and contributed it to the Kubeflow community, right? And it was essentially done to enable that ecosystem with leverages operators as the core mechanism of deploying workloads on Kubernetes or OpenShift, right? And then Red Hat colleagues came and did an excellent job of taking it forward and ensuring that, that becomes also, first-class citizen on OpenShift. So you can also deploy, Kubeflow as a first-class citizen on top of OpenShift, right? But that operator can be used not only to deploy on these two platforms, right? You can use that operator to deploy the way you are using, if you are using Kubeflow currently, to deploy in GCP, AWS, Azure, etc., right? So if you're into that ecosystem and if you like the benefits which operators bring, and for some folks, it's not exactly clear. So let me, just highlight one point. With something like Kubeflow or CLI tools which you are running on your machine, you're probably deploying, but then you're disconnected, right? It's not actively monitoring your Kubeflow clusters. It's not actively taking any actions if anything is going wrong on your Kubeflow clusters, right? And that's where operators shine, right? They have the operator lifecycle manager framework. The benefit which it brings is essentially giving you tools that, once you deploy Kubeflow through an operator, the job doesn't get finished after the deployment, right? It's essentially monitoring your Kubeflow deployment and taking actions if something has gone down, right? Trying to restart it, or you can configure things like send me an alert, right? So essentially managing the whole life cycle of it, right? And definitely going to the fact that you can then add more intelligence around updates and upgrades as part of it as well, right? And because of that, right, that one action also enabled the Open Data Hub team to actually do the great work they have done to make Kubeflow first class citizen and OpenShift, but also standardize the deployment and management of Open Data Hub exactly in the same way as the Kubeflow operator, right? So which leverages under the covers KF customized KF dev combination, which we use into the Kubeflow community, right? So now you have a version where you can deploy both using exactly the same mechanisms, the same operators which are built on the same architecture of KF dev, and mix and match, right? And I'll start skipping some of the details about the components which are available in Open Data Hub. As I mentioned, the slides are there. There is opendatahub.io, the website where you can go and get more details around that, right? But typically, once you have them in OpenShift, right, you will see the deployment spread out like this, right? So for example, things which you probably don't see in Kubeflow ecosystem, like Kafka, provided by the Strimzy operator or superset, or Airflow, they're all enabled by this as well, right? So superset, I mean, if you're probably working on the data science, you're probably familiar with it. It's hugely popular for data analysis and manipulation on top of relational DBs, as well as charting and graphing capabilities. Spark, I think we are all all familiar with, and majority of the users use Spark, right? So that's also enabled. There are two versions of Spark. One is a dedicated Spark operator, which enables to run Spark in dedicated mode, but there is also the serverless mode, which is based on the Spark on K8s operator, which is now also provided as part of the Kubeflow community. Airflow, I believe a lot of us do look at Airflow from an ETL perspective, right? And that's where Airflow has a lot of, I would say, specialization. So that's also available as part of the Open Data Hub install if you're interested in it, and by virtue of it, available as an operator. Now, Hive is something, right, which is very popular into the Hadoop ecosystem, right? It was a project which was initially started by Facebook to enable data analysts, right, to analyze the data in Hadoop, but in a more SQL-friendly way, right? So that's where Hive has a strong ecosystem going. So if you do have data residing in Cassandra or Hadoop databases, right, you can leverage this to essentially run a lot of analysis and graphing and querying capabilities. So also available as part of the Open Data Hub architecture. Right, so I think what we said, Open Data Hub very strong on the data side. We have Kubeflow, which is very strong on the machine learning and AI side. You bring them together, and what you get is an end-to-end data machine learning and AI platform, right? So it's available, through Operator Hub, right? And if you need more details around how to get going this with, bringing both of these projects together in one single consistent way, please contact us. Go to opendatahub.io, or reach out through Slack and others. Okay, so I think this is brings me to the end of my presentation at this particular point in time.